Hello, in this video we're going to complete this complex numbers review page. This is on the back of this one here, the properties of complex numbers. So we're on the back here. Complex numbers are defined as numbers where we have both a real part and an imaginary part. So A, whatever number was in place of A, would be the real part of the complex number, and the BI would be the imaginary part of the complex number. So we kind of have these two different sections going on. So in these notes, I'm going to be doing a lot of like color coding. Just beware of that because there's a lot going on here. I really like the look of these notes. It's just more fun, but again, just makes it kind of different. But in order to keep track of things a little better, I'm going to be using colors. So you could do the same if you want to. It's up to you, but it might be helpful. We're going to start in this top left corner box here. And so here we're going to write that the imaginary unit can be used to write the square root of any negative number. And so, for example, we know that I is equal to the square root of -1. That's like the definition of I. And then when we have I squared, because of that definition of I squared equals -1. Because if I were to take this and square it, I would just get -1. So if we pretend that r is a number, if I had the square root of -r, I could rewrite that so that r is positive by taking the I out. So here's an example. Like if I had the square root of -10, I could rewrite this as I radical 10. Of course, if your radical can simplify, you should do that. We are going to now look at some examples. You are welcome to, add anything that you want to this page before we move on. We are going to look at some just examples of that. So when I do the square root of -3, we can rewrite this as I radical 3. So you can simply make the number inside positive as long as you take the I out to represent the fact that we are square rooting a negative. If I were to show all of my work on this, I would rewrite this as radical 3 times radical -1. And we all know that, the radical -1 is equivalent to I. So that's kind of where this comes from in terms of like the reason we can just take the I out. For number 2, we'll kind of do the same thing. I could rewrite this as I radical 24, or I could rewrite it fully out like as, having the square root of -1. But I'm going to go from here. So we're not done though because radical 24 does simplify. I'm thinking of if there's a perfect square that can go into 24. So I'm going to say 24 can divide by perfect square. I'm going to rewrite this as I radical 4 times radical 6. Because the square root of 4 is 2, and then we'll have I and then radical 6. We always put the whole number out front if we have one. And so this radical 4 is what became the 2. And now we're looking at example 3. I want you to try this one and pause the video. I'm going to go ahead and go over the answer, but please pause it and try it. In this problem, we are squaring both the I and the radical 5, so you can think of this as almost squaring both of these things here. Because there's no addition or subtraction involved, I am allowed to do that. I don't need to expand it out. But because anything square rooted squared cancels out. So we know, for example, that radical 5 squared is just going to be 5. And then we also have to square the I, though. So we actually end up having 5I squared. We know that I squared is just the equivalent of -1. So this one ends up just equaling -5. So we just completed the example section for imaginary numbers. Now we are going to look at some operations. So take a minute to finish up your notes here. Okay, so let's fill in first this how-to section. All right, we're going to add or subtract the real parts and the imaginary parts separately. So I just really wanted to emphasize here that we must do these like terms, right? So the real parts in this adding example, like the 8 and the 5, those will combine, and then the i's will combine as well. So the imaginary parts are going to combine completely separately from the rest. Where we have our parentheses, the parentheses end up being not as relevant just because it's adding, so they're not as important here as they would be with subtraction. So we can add the 8 and the 5 together because these are the real parts. And then we're going to combine negative I and 4i since these are the imaginary parts. So 8 plus 5 is 13. And then negative I plus 4i is 3i. So this is my answer. If I wanted to show a little bit more work, you don't have to write this part, but for the sake of the notes, I'm going to show a little bit more here. So what I did is I took the 8 and the 5, and so we did 8 plus 5. And then we took the negative I and 4i, and we did negative I plus 4i. So that's kind of how we ended up with the answers that we did. With subtraction, though, I have to be a little more careful because we are distributing this subtraction sign to both terms here. So we end up having 7 minus 6i minus 3 plus 6i because I have minus a minus here. You could also write this as minus negative 6i, but for me, it's easier to just go ahead and simplify that as plus 6i. So we do have things that kind of cancel out here. We see the 6i is going to cancel with negative 6i, but I can combine 7 and negative 3 to get 4. Negative 6i and 6i make 0i, but anything times 0, even if it's an I, equals just 0, so I don't really need to write that. My final answer is simply 4. So we just finished adding and subtracting. We are going to now look at multiplying and dividing, but take a second here to finish up your notes. All right, adding, subtracting is done. Here, let's move on to multiplying and dividing. We are going to multiply, obviously, using the distributive property. And so in this example here, we would do 9 and distribute that to the negative 4 and the 7i. And so when I did that, if I distributed the 9 to both of these terms, I would get negative 36 plus 63i. So this first part comes from that first distribution. Then I would take the 2i and distribute that to both of these terms in the second. So when I do the negative 2i distributed times negative 4i, I'd get plus 8i. And then negative 2i times 7i would be minus 14i squared. So this part comes from the second distribution that I did. I'm just going to clean this up a little bit here for clarity. All right, now I am simplifying, combining like terms, yada, yada, yada. So I'm going to just rewrite this really quickly as negative 36 plus 63i plus 8i, and I'm going to go ahead and replace the I squared with negative 1. If I were to combine the 63 and the 8i, I would have negative 36 plus 71i, and negative 14 times negative 1, that would be the same as positive 14. And then I can also combine the negative 36 and the 14. When I do negative 36 plus 14, I get negative 22. and then I have plus 71i still. Since that's an imaginary part, we don't want to combine that. So let's circle this as our answer to that multiplication problem. So let's do a division example. So to divide, we are multiplying the top and bottom by the complex conjugate of the denominator. So conjugate, conjugate. So in this example that we've given, the denominator is 1 minus 4i. And so the conjugate of that would be 1 plus 4i. So we're going to multiply by 1 plus 4i, 1 plus 4i. We do that to top and bottom. In the top, remember, I have to distribute the 7 to both of these numbers. And so when I do that, I get 7 times 1 is 7. 7 times 4i is 28i. I also have to distribute the 5i to both numbers now. So 5i times 1 would be plus 5i. And then 5i times positive 4i would be plus 20i. I squared, sorry. And then in the denominator, we know that when we multiply conjugates, the middle terms cancel out. Like, for example, in the top, how we ended up with 28i and 5i. If they're conjugates, those parts cancel out. So what I end up getting here when I multiply this is 1 minus 16i squared. If you would like me to work that out, I can do it down here right now, but you can fast forward if you don't need it. 1 times 1 is 1. 1 times 4i is 4i. Negative 4i times 1 is minus 4i. And then minus 4i times 4i would be minus 16i squared. And so these middle parts, as you see, cancel, and I end up with just 1 minus 16i squared, which is what I had. Okay, let's go ahead and wrap it up, though, now that I showed you where that comes from. We are just simplifying here, replacing I squared with negative 1, etc. And so when I come down here to simplify, maybe I'll just write that in case you need the notes. We have 7 plus, I'm going to combine the 28i and the 5i. And when I do that, I get 33i. I'm going to replace the I squared with negative 1. In the denominator, I have 1 minus 16, and then I can replace the I squared with negative 1. So really, I have 1 plus 16. So I know in the bottom, I'm going to end up with 17. In the top, I know that I ultimately have 7 minus 20, and so that's going to give me negative 13 for my real numbers. So again, that's coming from the 7 and the negative 20. And then I also still have the 33i. And this doesn't really simplify anymore at the moment. So we're going to stop here. And so this would be the conclusion of the multiplying and dividing section of our notes. So I'm going to just get my color coding finished, and then we'll do the last part. Alrighty, we are moving on to this last little section. We're going to have like kind of a summary, like solving with it. And I did just want to put a little bit more notes here for complex conjugates, which I know we just used an example of, but I do want you to write A plus BI and A minus BI. These would be our complex conjugates. And I do want to emphasize this part here, which says when multiplied, complex conjugates will always be a real number because the i's will always cancel out here. Last section is when will I see these in terms of like this class. Oftentimes when solving a quadratic equation, the solution will contain an imaginary number. This is very, very, very common. Maybe not for you so far because your math teachers purposely choose ones that don't have imaginary number solutions because you haven't learned it yet, but it is actually pretty common. So this happens most often when we're solving a quadratic. Here is an example. So in this problem, we would ultimately subtract 33 first from both sides. I would get 5x squared equals negative 30. Then I would divide by 5. And I get x squared equals negative 6. And then when I square rooted both sides, I would get x equals positive or negative radical negative 6. But of course, it's not simplified if we still have a negative in the radicals. So I would need to rewrite this as positive or negative I radical 6 for my final answer. So make sure you're always looking for negatives inside of your square roots here. I'm also going to put a note here that you should simplify the radical if necessary. In this problem, you couldn't, but most of the time you can. So all I did to wrap up this review is I highlighted all of my key points. I recommend pausing the video, filling in all the information you missed, highlighting key points, and you should be good to go. Thank you.